Okay, so what we're going to talk about right now are how to draw orbital diagrams and write electron configurations, because when we are trying to figure out what makes an antioxidant special, what we're really talking about is how the electrons are arranged around the nucleus of that particular atom or molecule. So it's really helpful to understand the electron configuration. So if you recall, electrons kind of inhabit these areas of probability around the thingamabob, nucleus, there we go, in the atom. We referred to them kind of like rooms where we could kind of guess where the atom is, where the atom spends most of its time. So we had this area over here, this first energy level right here. Whoa, sorry, didn't mean to move the whole screen like that. We had this first energy level here. Oh, sorry, my pen is white. That's not very helpful, is it? So we had this first energy level here at the bottom, the 1s, which was shaped like a sphere. Then we had the 2s, and it was different because we had these two sublevels. The first sublevel was the s, but the second sublevel was actually the P, which was divided into 3 rooms. Okay? Now, once we go above that, once we get to the third energy level, we had access to this next set of rooms, the D, which had 5. Now, each one of these orbitals can hold 2 electrons. So each one of these rooms can hold 2. So we've got 2 here, 2 here, 2 here, 2 here, and so on. But here's the thing. If we look at P, each of these P orbitals holds 2. So altogether, the P sublevel can hold 6. The same is true, or the same idea is true for the D sublevel. Each one of them can hold 2. So altogether, the D sublevel can hold 10. Whereas the S sublevel can only hold 2. And this is where that 2, 8, 10 things comes from that you talked about in elementary and middle school. So it's helpful to keep in mind that each floor of the electron hotel, if you will, can only hold so many electrons. Now, this brings us to the idea of configurations, which configuration is nothing more than the address of the electron, or how they're organized. That's the way I like to think about it, how they're organized. Okay? So this right here, this 1s1 with the superscript, is called a configuration. This right here, the orbital diagram, is actually a picture of what's going on. Okay? Where we use an arrow to represent an electron. So I'm going to draw one up here just so that I've got some more space. So I've got 1s. This little arrow right there, and we usually draw what's called a half arrow. This little arrow right here represents 1 electron. Okay? And if there was another one here, that would be 2 electrons there. But let's go back and take a look at the configuration. The 1 tells me the value of the principal energy level. And in the upper echelons of chemistry, we refer to it as N. So that tells me what floor of the electron hotel I am on. The letter S tells me the type or shape of orbital. Okay, in this case, S stands for sphere. Now there are only 4 types of shapes that we talk about. We talk about S, we talk about P, we talk about D, which we've seen all 3 of these, and then there's F, which is just too much to draw. I mean, there are pictures of it, but then you have this 1 right here, this exponent 1, and that refers to the number of electrons in the orbital. So how many are actually in the room at the time? So when I see 1s1, what that's telling me is there's 1 electron in the S sublevel on the first floor. Okay? Now, let's go ahead and take a look at some of these things right here. Here I have 1s2. Okay? This is helium. Helium has an atomic number, or Z, of 2. Now, just for reference, hydrogen, its electron configuration is 1s1. Helium's is 1s2, which makes sense because it has 1 more electron than hydrogen. And if we remember, that S sublevel can hold 2 electrons. So it gets 2 arrows in its orbital diagram. The problem comes when we get to lithium. When we get to lithium, lithium has an atomic number, or Z, of 3. Now those first 2 electrons are going to look like helium's. But then we've got that 3rd electron that needs a home. So we have that, I'm going to draw it this way instead. So we have that 1s that's got 2 electrons in it. So now we need to go up to the 2s, which is slightly bigger, and that's where that other electron goes. So it goes up to the 2s level and fills up. And this is according to the off-bow principle. The off-bow principle states that you fill the orbitals from the bottom, one at a time. Okay, we start at 1s and we work our way up. So once 1s is full, we go to 2s. Now beryllium has an atomic number of 4. So it goes 1s2. There's still some room in the 2s orbital, so it gets 2s2. So we put that that 4th electron in this 2s orbital. But now the 2s is full. So 1s is full, 2s is full. So when we get to boron, which has an atomic number of 5, we have 2 in the 1s, 2 in the 2s, but now we need somewhere for that 5th electron to go. So we go to the next set of rooms, now that we've filled up 1 room, and we go to the penthouse. And we start putting the electrons in those orbitals in the 2p, because 2p comes after 2s. And our electron configuration reflects that. 1s2, because there's 2 electrons in the 1s. 2s2, because there's 2 electrons in the 2s, and 2p1, because there's 1 electron in the 2p. Now, carbon, which has an atomic number of 6, the first 5 electrons are going to look like borons. However, that 6th electron, I want you to notice, it goes in a box by itself, because according to Pauli's exclusion principle, Pauli's exclusion principle and Hund's rule, so these two rules together kind of indicate that the electrons are going to go one by one per orbital. They're not going to pair up until they have to. Everybody on the bus wants their own seat. Okay? Everybody on the bus wants their own seat. Everybody in the hotel wants their own room. They're not going to pair up until they have to pair up. If they don't have to, they're not going to. And our electron configuration shows this. 1s2, 2s2, 2p2. Now we get to a little more complicated. Nitrogen, which has an atomic number of 7. We've got 1s2, 2s2, and now we've got 2p3. And notice they're all by themselves. They're not paired up yet. So keep that in mind. Okay, that's Hund's rule. The electrons are going to be unpaired until they pair up. But now, every orbital has an electron. So the next one will pair up. And I know it should say pairs up, but I ran out of room, so bear with me. Okay, which makes sense. When we have oxygen, it has an atomic number of 8. So the first two here, 1s2, 2s2, 5, 6, 7. But now that 8th electron has to go back to fill in the first orbital. But notice it's going the opposite direction. This has to do with Pauli's exclusion principle. When electrons have to pair up, they are going to face opposite directions. And this has to do with electromagnetic repulsion. Electrons are going to, for reasons that we're not going to get into, the electrons have to have alternate spins. Or have to have, I'm sorry, not alternate, opposite spins when they're in the same orbital. It makes them more energetically stable. Okay, so once they start pairing up, they start having opposite spins. And we usually draw them all going up at first, but they can all go down as long as they're going the same direction. Nobody's going to like mark off for it. And if they do, they're bums. Yeah, you heard me, I said it. Okay. We see the same thing with fluorine, which has an atomic number of that number that's 1 greater than 8, 9. Thank you. Okay. 1s2, 2s2, 2p5. We've paired up our electrons again. And when we go back and look, our electron configuration is telling us this. 1, 2, 3, 4, 5. Or 1s2, 2s2, 2p5. The fact that this number is greater than 3 indicates to us, the scientists, that they are unpaired. That they are paired. That there are 2 that are paired. Because I know that P can hold a maximum of 6. That's just something I remember from chemistry class. And if we look at neon, that makes sense as well. Neon has an atomic number of 10. And if I look at the 1s, so 1s, 2, 2s, 2, 2p, and there's 6 electrons in there. And all those together give me the electron configuration. So this is how we build the electron configuration from the orbital diagram. Okay. So here it is. This kind of shows you, this is how we use the periodic table. It just kind of shows you what the last part of the configuration is. what the last part of the configuration is. So let's say I want to know the configuration for phosphorus. I know that it's going to end in 3p3. So I trace backwards, and here's the last full one. 3s2 was the last full one, so I include that. 3s2. I trace back. Neon was the neon was the last full one before magnesium. So I put 2p6. I know it's full because it says 2p6, and 6 is the most that it can hold. Trace backwards. Beryllium is the last full one before neon. So I put 2s2. I keep tracing backwards. And helium is the last full one for that. And that's 1s2. And that tells, since 1s2 is the very bottom, that gives me the electron configuration for phosphorus. Okay? So that's how we can use the periodic table to build an electron configuration and work our way backwards. Now, one thing I want to draw your attention to is this is in the first column of this blue part, 1, 1. This is in the second column of the blue part, 2, 2. This is in the third column, 3, 3. You noticing a pattern? Hopefully. And with the exception of helium, we see a pattern there too. And in this pink part, this is the first column, we see a 1, 1, 1. We see a 2, 2, 2. Okay? Now, the order of orbitals, or I'm sorry, the order of sublevels is very confusing because it goes in order until you get to the first D, the first 3D, because the 3D doesn't come after 3P the way you think it should. It actually goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on and so on and so on, up this list in energy. Okay? That is a lot to remember. It's hard to memorize that. I tried when I was in high school. I tried when I was in college. I tried later in life, and I just couldn't do it. I get to about 4D and forget. However, there is this cool little, what's called the diagonal rule. That's a good way. I sketched this on everything, every test that had electron configuration when I was in high school and college. Okay? The diagonal rule, you write everything. You write, 1s, 2s, 3s, 4s, and so on. 2p. What we have to remember, though, is that the first time p shows up is 2. The first time D shows up is 3. The first time 4 shows up is F, and so on. Okay? And then all you do is follow a diagonal line, and it tells you the order. So 1s, then 2s, then 2p, 3s, 3p, 4s, then 3d, 4p, 5s. And this is really, really handy because once we get past 6s, we introduce 4f. Okay? So this is a good handy rule to keep around. Okay? The diagonal rule is fairly straightforward and easy to memorize. Okay? It's a good mnemonic to get started with. The periodic table is also a great way to remember electron configurations. So you have this section over here that is called the P block. Now, since it is called the P block, everything in there, the last part of its configuration is a P. Like this is 3p2 because it's in the second column of the third row of the P block. Okay? This is 5p5. I don't know what that element is off the top of my head because it's in the 5th column of the 5th period of the p block. Okay? The same is true over here. This is called the S block. And one thing I want you to notice, I should not have written that right there. Okay. One thing I want you to notice is 1s, 2s, 3s. These numbers, whatever period it's in, is the number that goes in front of s. And the same is true for p's. I'm going to pick another color real quick, so bear with me. I've got 2s, 2p, 3s, 3p, period 4, period 4, period 5, period 5, etc. Okay? The only place it gets tricky is what we call the D block, which are transition elements. And down here, we call this the F block. Okay? In this case, it's the period minus 1. So 3D, 4D, 5D, 6D, etc. And we'll do a couple of examples to help with this. So an orbital diagram and electron configuration for sulfur, which has a Z of 16. And that means its atomic number is 16, which means it has 16 electrons. So let's switch to black. So it's got 16 electrons. Now, because of the diagonal rule, which we're not going to need to go further than that, so I'm not drawing further than that. Okay. I know that I'm going to have 1s. The first 2 electrons are going to go there. I know that I'm going to have 2s. So the next 2 electrons are going to go there. I know I'm going to have 2p. 1, 2, 3. And 3s. Now remember, our seats only get filled up one at a time. Our rooms only get filled up one person at a time, or one electron at a time. So 2, 4, 5, 6, 7, 8, 9, 10. 11, 12. Then after that is 3p. 1, 2, 3. 12, 13, 14, 15, 16. So that's what my orbital diagram looks like for sulfur with 16 electrons. It has 2 unpaired electrons, which will be relevant when we talk about radical electrons. So my electron configuration is 1s2, because there are 2 electrons in the 1s orbital, 2s2, because there's 2 electrons in the 2s orbital, 2p6, because there's 6 electrons in that one orbital, 2p, thank you, 3s2, and 3p, I don't know why that looks like a D, 3p4. So there's my electron configuration for sulfur. Okay, pretty straightforward. Now, our orbital diagram and electron configuration for zinc. Ooh, zinc has an atomic number of 30. So I'm just So that means it has 30 electrons. I'm going to draw my diagonal rule real quick. I know I'm going to need a lot of them. So I'm going to go to 4. Okay. So I've got 1s, which is 2. I've got 2s, which is 2, which brings me up to 4. I've got 2p and 3s. 1, 2, 3. 2p, 3s. Now remember, we fill up the orbitals one at a time for a p sublevel. 4, 5, 6, 7, 8, 9, 10, a third of the way there. So next one, okay, that's 12. Hold on a second. 3p. 12, 13, 14, 15, 16, 17, 18. And then 4s, 19, 20. Now, when we go back, we're starting at the 3D. Now, remember that 3D has 5 orbitals. Okay? The D sublevel has 5 orbitals. So 1, 2, 3, 4, 5. Okay, so I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So there's my orbital diagram for zinc. Then when I convert that, all I do is I add the exponents that says how many electrons are in that sublevel. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. Okay, that is all there is to coming up with the electron configuration from the orbital diagram. Now, lanthanum is a lanthanide, go figure, with an atomic number of 57, and that means that it has a lot of electrons. It has 57 electrons. So we're going to take a sort of shortcut here. 57 electrons. If we go back a few slides and we look, lanthanum is right here on the periodic table. That means it's in the F block. I'm going to need to use my diagonal rule until I get to 4F. Okay. So 1s, 2s, 2p, 3s, 3p. Now, note the diagonal rule doesn't take a lot of time to write out, and it helps. It really helps figure out the order of things. But here's the thing. We're tempted to stop there because, oh, I've got the 4F. But remember, we're going to have to go down and then back up to 4F. So I'm still going to need 5S, 5P, 5D. Okay, I'm still going to need 6S. Okay, because I've got to go down there before I go back up to 4F. Okay, so keep those things in mind. Oh, hold on, I'm trying to use my undo button so I don't have to. Okay, So this is where it comes in handy to know how many electrons go in each orbital so that we can count them. For instance, 1s2. We know that's going to be full because we're trying to get here. We know 2s is going to be full. We know 2p and 3s are going to be full, and 2p can hold 6 at most. 3s can hold 2. We know 3p and 4s are going to be full. Oh, 4s, duh. Here I was going on about the rules. 3d. We need to remember that d can hold 10. 3d 10, 4p 6, 5s 2, 4d 10, 5p 6. Hold on a second, I'm going to move this. Whoa! That's unfortunate. That sucks. I tried to move it, but it's not letting me move what I want to move. I am sorry. So you have to bear with me. So the rest of our configuration, which is super long at this point, 5p and then 6s2, and then we know that lanthanum is the first element in the F block. So since it's in the first column of the F block, it's 4f1. Okay. Later we will come up with a way to shorten that process considerably so that we do not have a line that is so long I have to draw a wicked arrow. Okay. So that is how you write electron configurations and how we can use the periodic table as a shortcut to electron configurations. And hopefully this helps. And if you have any questions, please make a note of them and let me know and carry on.